In this section, we learn about inertial and non-inertial frames of reference. Again, let's consider a train's compartment with a table and a block. And let's say that the train is not moving, that is, it is stationary. And if we throw the block directly upwards, we will see that it comes back to the same point where it was thrown up. Now let's look at another case. And this time the train is moving with a constant velocity. Okay, it's moving with a uniform velocity. So if we repeat the same experiment inside the compartment, what do we expect to see? Remember, the train is now moving with a constant velocity. Okay, well, the block comes back down again at the same point. And if you were traveling in a train and once the train reaches a constant velocity, you can try to throw a ball up and see for yourself what happens. It will come back in your hands, and that's what happens, right? Now let's watch this experiment from the Earth's frame of reference. At time t is equal to 0, the ball is thrown straight up in the train's frame. So in the Earth's frame, the motion of the block will look something like this. And the block hits the same point on the table from where it started. In the Earth's frame, why didn't the block just move straight up? Why did it also have a horizontal component of the velocity? Well, the thing is that just at the time of projection, the block was in contact with the train. Hence, it was also moving at the same velocity as the train. And when it was thrown up, it also continued to move horizontally because of the velocity it got from the train. Now, there is the force of gravity acting on the block which brings it down again. But is there any force acting in the horizontal direction? Well, no, right? And that's the reason why the block continues to move with the same velocity as the train, because no external force is applied in that direction to change it. And the train also continues to move with the same velocity, because we already said that in this case the train travels with a uniform velocity. Hence both of them travel equal distances in equal time. Hence the block lands back at the same place on the table. Now in the train's reference frame, the train itself is stationary, right? And there is no force in the horizontal direction. And because there is no horizontal velocity of the train itself, in the train's frame of reference, the block's horizontal velocity is also 0, right? It will only have a vertical velocity at the point of projection. So because its initial horizontal velocity is 0 and no force acts on the block in the horizontal direction, hence it continues to move with 0 horizontal velocity throughout its motion and lands back at the same place from where it was thrown up. So these kind of frames or these kind of reference frames are called inertial frames of reference. Both the train moving with a constant velocity and the earth prove to be inertial frames of reference. So what is an inertial frame of reference? Well, the inertial frame of reference is one in which the law of inertia holds. And what is the law of inertia? Well, if you recall, the law of inertia states that any body at rest or moving with a constant velocity will continue to remain at rest or move with a constant velocity unless an external force is applied to it, changing its state of motion. So if no force is applied to it, the body will continue to move as it was moving or will remain at rest if it was not moving. So now you know why we said that the train's frame moving with a constant velocity and the earth's frame are both inertial frames of reference, because in the train's frame, although the vertical component of the velocity changes, but that's because the force of gravity is acting on it. But in the horizontal direction, no force acts, hence its horizontal velocity in the train's frame remains 0. Similarly, in the Earth's frame of reference, the block is moving with the same velocity as that of the train, just at the point when it was projected up. And because there is no force in the horizontal direction, the block continues to move with the same velocity as that of the train. even during its flight and lands back at the same spot on the table, which itself was moving along with the train at the same velocity. And the only force that was applied during the time of projection or throwing up of the block was directly upwards, right? Hence, even in the process of throwing, no horizontal force is applied. So, in the inertial frame of reference, that is, when the train is stationary or moving with a uniform velocity, we mark the point directly underneath the block and release it. And because we didn't give it a horizontal velocity, it falls at the marked spot, suggesting that due to the lack of any horizontal force in the train's reference frame, it continued to have zero horizontal velocity during its flight. Otherwise, it would not have hit the marked point, isn't it? Now consider the case when the train is accelerating in the direction shown. As earlier, we mark the point on the table directly under the block. And when we release the block, it kind of moved back and didn't hit the marked point or the marked line on the table. So the block got displaced, and this amount of displacement really depends on how much is the moving frame of reference accelerating, which is the train in our case. More the acceleration, larger is this displacement. But was there any horizontal force applied to the block? Well, no, right? Nobody touched it, or there is no force field in the horizontal direction. But it did move, and because it moves in a finite time, its velocity initially was definitely zero because it was just dropped, and it changed over time, right? Because now we do see some displacement in a finite amount of time. Basically, the block moves in the horizontal direction from zero initial velocity to some finite velocity, okay? So does the law of inertia holds here? Because we did not apply any force in the horizontal direction. So even though no real force acts on it, the velocity of the block changes. Hence the law of inertia does not hold good when the train is accelerating. So an accelerating frame of reference is a non-inertial frame of reference because the law of inertia does not hold good here. And because in this frame we cannot explain this motion, hence we bring in the concept of a pseudo force, which is a fictitious force and does not really exist. But it's needed to explain this kind of movement in accelerating frames of reference. So a frame of reference is inertial only when it is either stationary or moving with a uniform velocity. But an accelerating frame of reference is a non-inertial frame of reference in which the law of inertia and hence the Newton's laws do not hold good unless we bring in the idea of a pseudo force. And I will suggest that you don't generally choose accelerating frames of reference while solving problems. Rather stick to the earth or any other inertial frame of reference, at least initially, unless you know what you're doing. So if the earth's frame is inertial, we should be able to explain the motion of the block when the train is accelerating from the earth's frame of reference without bringing in the idea of a pseudo force. So can we do that? From the earth's frame of reference, the motion of the block is still seen to be similar, the path being a parabola, just like we saw in the case when the train was moving with a constant velocity. So let's zoom in a little to see what's actually happening. Let's look at the first case when the train was moving with a constant velocity. So the table is moving with the train and the block is not in the air actually. Somebody must be holding it inside the train, isn't it? Which we are not showing here. And he must be standing on the train. So he would also be moving with the same velocity as the train. So the block in his hand would also move with the same velocity as the train. Now remember, right now we are observing it from the Earth's frame of reference. So just before the block is dropped, it is moving with some velocity. And the table would also be moving with the same velocity. Both these velocities being equal to that of the train. And because the block and the table continue to move with the same horizontal velocity, the block will hit the table at a point exactly under the block when it was released, which is, let's say, the center of the table. And if we were to draw the path followed by the block, it will look something like this, which is a parabola and is a path of a projectile, which we'll study in detail in the next chapter. Now let's look at the block from the Earth's frame of reference when the train is accelerating. So let's say that at this point of time, we are about to release the block. But at this time, is the velocity of the block and the table same? Well, of course, right? As long as the block is not released, it will also experience the same acceleration, which would mean that both the block and the table will have the same velocities at all times until the block is released. So at the time of release, the velocity of the block is same as the table. Now let's mark the point on the table which is directly under the block. Now we'll watch the motion of the block and the table in slow motion again. After a moment in time, what is the horizontal velocity of the block? Well, it remains the same as it was a moment ago, right? But by this time, the velocity of the table would have increased because it is still attached to the train and hence accelerating. Then after some more time, the block still moves with the same velocity in the horizontal direction while the table's velocity increases further, and it continues until the block hits the table. Now if you want to see it more mathematically, then let's say that this was the place from where the block was dropped. Because the block moves with a constant velocity, let's say v0, which is also the table's and the block's horizontal velocity when it was dropped, and the acceleration of the block is 0 in the horizontal direction. Hence, if the time of flight is t0, the block is displaced by v0 t0. Now, the initial velocity of the table and the mark at the time when the block was dropped is also v0. But it continued to accelerate with, let's say, an acceleration a. Hence, the displacement of the mark in time t0 is v0 t0 plus half a t0 square. We have applied the second equation of motion, which means that it got displaced by half a t0 square more than the block. So now we are able to explain this motion of the block from the Earth's frame of reference without bringing in the idea of pseudo-force. So if we look from the Earth's frame of reference, it is not that the block was moving backwards. It was just that the train's or the table's velocity kept on increasing. So the point that we had marked on the train kept on moving faster than the block, and hence we got the perception from inside the train as if the block was going backwards. But in non-inertial frames or accelerating frames, it seems like the block moved on its own in a direction opposite to that of the acceleration. In your personal experience, when you are moving at a good speed and suddenly apply the brakes, you tend to move forward due to your inertia of movement. Because you are moving at the same constant speed with the car, and when the brakes are applied, your lower body, which is moving with the car, tries to stop with the car due to the application of the brakes. But your upper body still tries to maintain its earlier velocity before coming to rest with the car. But in the reference frame of the car, no force was ever applied to you. So why did you move forward? Sometimes solving a problem in an accelerating frame is much easier than visualizing it in the Earth or an inertial frame of reference. But in general, I would advise not to use non-inertial frames of reference for solving problems, unless you are absolutely sure about pseudo-force. And why does it come in the picture? And we'll talk about forces in a later chapter. Now, before we end this chapter, there is one little thing that must be pointed out. Is the Earth's frame really inertial? By the way, you may have to come back to this part after you understand circular motion, especially the dynamics of it, but we'll cover that part after introducing the idea of force. Meanwhile, you can take some of my words for granted. Now we know that the Earth spins or rotates about its axis, and rotation also causes acceleration. So the Earth's frame is rotating, hence it is also accelerating. So how can we treat it to be an inertial frame of reference? Well, let's first calculate the value of this acceleration due to the rotation of the Earth. If you don't understand how we are calculating it, don't worry about it. Just look at the comparison that we'll do, and you will be able to do these calculations once you are familiar with some more topics later. So the radius of the Earth is about 6400 kilometers, which is almost 6.4 million meters. And the angular velocity of the Earth is known to be this. So the centripetal acceleration, which is what may cause the trouble, is omega squared into r, which turns out to be 0.034 meter per second square. And this acceleration points along the radius of the Earth. But the major component of the acceleration comes due to the force of gravity, which produces an acceleration of 9.8 meter per second square, which we know as acceleration due to gravity. So this value of the centripetal acceleration is much less than the value of g. Hence, we can kind of ignore it without causing much of a problem. Moreover, this acceleration is also directed along the radius of the Earth. Hence, any frames that we choose on the surface of the Earth will remain unaffected by this acceleration. So we can safely choose the Earth to be an inertial frame of reference, and we can ignore the effect of the rotation of the Earth on acceleration due to gravity. So with this we close this chapter, and I urge you to try out the exercises before moving on to the next chapter, which will be on projectile motion.